Let's go ahead and start. Let's go into Classroom destruct. So under the GitHub folder, there should be this document. Under the GitHub folder, under the GitHub link, this is just a summary of all the things that I think are valuable for you guys to know for the exam to cover. So be sure to check it out. It lists basically all those things that I think are valuable information for you. Let's see, you should also know, but most importantly, are these links here at the bottom. There's 4 links to 4 different finals, which I'll go over in class right now, or I'll start going over in them right now. So we're going to start with the first one over here, with the one, the third link. And this one's from Harvard for CSCI 3119. So, I like this one because there's a lot of multiple choice questions as well as a lot of, there's a number of good coding questions. Oh, come on. So, this one is a 2-hour exam just like ours is, so we should be able to get most of it done. So we should be able to get it done well before class is done, right? Just because there's 2 hours to allot to it, right? So, let's see. So first part is multiple choice. They had this weird clause where you can specify 2 different choices for your multiple choice and get partial credit. That's one way of averting it. That's one way to avert a curve, by making sure that there's partial credit on the multiple choice questions if you're stuck. So let's go ahead and take a look. All right. So question number 1. Suppose that items A, B, C, D, E are pushed into that order on an initially empty stack S. S is then popped 4 times. As each item is popped off, it's inserted into a queue. If 2 items are then removed from the queue, what is the next item that will be removed from that queue? If you are trying to solve this in the head, if you're trying to solve this in your head, congratulations, you are going to lose points. Because, most likely. Because it's much easier if you're dealing with stacks and queues just to draw stuff. Right? So let's go ahead and draw a stack. Insert A, B, C, D, E into the stack. Right? Then the next thing to do is to pop it 4 times and insert each of these popped items into an initially empty queue. Okay? So pop off E and queue it, pop off D, pop off C, pop off B. Right? And then it says to DQ twice. 2 items are then removed from the queue. You can only remove from the front of the queue. So remove E, remove D. Right? Remove the front of the queue twice. What's left? What is the next item that would be removed from the queue if we were to remove an item? It would be C. So our answer there is C. All right. If the binary tree below is printed by a pre-order traversal, what would the result be? Now remember, pre-order traversal is handle myself, then my left side, then my right side, right? Handle myself, then the entirety of my left subtree, then the entirety of my right subtree, which themselves also handle it in pre-order traversal. Okay, so with that, what is the first value in a pre-order traversal? What should the first value be? 6, right? So we immediately know A and B are wrong. Okay. Next we have, for pre-order traversal, we need to go to our left side first. So that should be 17 next. So C is wrong. So it's either D or E. Now D, let's go ahead and just look. That's 6, 17, 22, 9, 4, 16, 12. 6, 17, 22, 9, 4, 16, 12. That is not pre-order traversal. That is in fact something called a level order traversal, or as you may have known it, or as you've just learned, a breadth first traversal, right? It is just simply traversed. So that is the kind of traversal. That is like the only traversal in a tree that doesn't use recursion. Okay, so we know that D is wrong, so the answer is E. All right, so now on to graphs. So a graph implementation that uses a two-dimensional array to represent the edges would be most reasonable in which of the following cases? So let's go ahead and review. There are two ways, hopefully you've watched the videos by now. There are two ways to represent a graph. There's two ways you can implement a graph. What are the two ways? Do you remember roughly what they are? Yes, adjacency matrix and adjacency list, right? So adjacency list, right? For every node, we have a list of all the other nodes it's adjacent to, and for a matrix, it's literally a 2 by 2, sorry, it's a n by n matrix or v by v matrix, right? Right, that looks something like this. And in an undirected graph, you have a 0 if no edge is present, and a 1 if an edge is present, right? So what is the most reasonable for which to use the following cases? So do you remember why you want to use it? Why we have adjacency list versus adjacency graph? Sorry, adjacency matrix versus adjacency list. Why would you want to use a list versus a matrix? Under which condition? Yeah.
List uses less memory.
List uses less memory under certain cases, right? That's the kind of, because there's an overhead for storing the list, right? And there's an overhead for storing the list and all the data in the list. It ends up being that basically that with a matrix versus a list, we want to use a list in a sparse graph where the number of edges to the number of vertices is right. Where basically the number of where the number of edges is on the same order as the number of vertices. That's a sparse graph. For instance, this is an example of a sparse graph. Let me go ahead and draw a bunch of nodes, right? No need to label them. Right, this is a fairly sparse graph. Like most of the nodes here have only have two connections, only two edges, right? There's about as many edges as there are nodes. That's a sparse graph. A dense graph, on the other hand, is something where there's a lot of other combinations, where basically most of the possible edges exist, right? Now, does anybody remember what the magical cutoff point for when you want to use an adjacency list versus an adjacency matrix is? It's about 25%. So once 25% of all possible edges exist, you want to have an adjacency. You want to use an adjacency matrix. Once there's 25% of all possible edges exist. How many possible edges are there? Well, let's take a look at our adjacency matrix. Right? It's n by n, or v by v rather, for a grand total of v squared possible edges. Those are all the possible edges that could exist in simple graphs, like the ones we're dealing with. So, yes?
Are you recording all this?
Yes.
Okay. Real quick, do you know the password for the sorting quiz?
The sorting quiz is not off the top of my head.
No.
Okay. And then so let's take a look at this. 1,000 nodes, 1,200 edges. That's a very sparse graph. Why? Because while there's 1,200 edges, there could have been up to 1,000 times 1,000, 1,000,000 edges. Could have been possibly 1,000,000 edges, right? There's a million possible pairings that you can do. So very few nodes are getting used there. On the other hand, 100 nodes, there's 100 by 100 edges, possible edges, or in other words, 10,000. So 4,000 out of 10,000, that's about what? That's 40% of all possible edges being used, so that's a dense graph. 1,000, again, 1,000,000 possible edges, 10,000 being used, still pretty sparse. And then over here, 20 edges out of 100 possible ones. They're also pretty sparse. So that's fairly sparse, but getting denser. So in this one, B is our best answer because that is the most, that is the densest graph out of all these. Okay. A binary tree is constructed of nodes using this class. So they have their left and right, and they only hold integers called going to be using just an int over here. So let's take a look at this method. And I love this question. Okay, I love this question. One of my favorites here. Consider the following method. Public static node mystery, node root. Takes in root, and it says if root.write is null, return the root. Otherwise, return mystery of root.write. So here we're going to consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what the method does. One passes reference to the root of the binary tree. Okay, consultant number 1 says, oh, that's easy. It returns the node, the last node visited in an in-order traversal. Consultant 2 says it returns the last node visited by a post-order traversal. And consultant 3 says it returns the last node visited by a level order traversal. Which of these opinions are correct regardless of the contents of the tree? Right, and it says 1 only, 2 only, 1 and 3, 2 and 3, but whatever. Right, so multiple of these could be correct. So let's go ahead and just consider about what this algorithm does. Right, it says if I don't have a right child, if I don't have a right child, I return myself. Otherwise, I return this call on my right child. So what this does is that essentially it starts at the root, and it essentially goes all the way to the right until it can't go any further to the right anymore. Right? That's all it does. So now what's special about the rightmost node in the tree? What is special about that node that this gets? It's the largest value. Yeah, it's the biggest node in the tree. Nothing bigger than it. If there was, we'd go to the right and find it. But there's nothing bigger than it because we can't go to anything to the right. So this returns, what this really does, a much more accurate statement than anything these tech consultants say is that it returns the largest value in the tree. That's what mystery does. So let's go ahead and see how that compares to what the consultant said. 1, it returns the last node visited by an in-order traversal. Well, the last node in an in-order traversal is the largest node in the tree, right? The largest value in the tree is the last thing in an in-order traversal. So 1 is always true. What about 2? It returns the last node visited by a post-order traversal. Okay, post-order traversal is what? Handle my left subtree, handle my right subtree, then handle the root. So the last thing in a post-order traversal is the root. So 2 is not correct because the only times that 2 would be correct is that if you had a tree that looked like this. Here's the root of the tree, and you had a left subtree. That is the only way that number 2 would be correct. Those are the only cases in which number 2 would take correct. Consultant number 2 needs to double check data structures classes again. So consultant number 3 says it returns the last node visited by a level order traversal. Right? In level order, right, that's our breadth first search. Right? And if you drew a perfect tree, like this consultant probably did, you probably would get something that looked like this. Right? So the last node in a breadth first traversal, in level order traversal, would return this last value, right? Right? So that seems on the face of it to be right, except, well, if instead we drew a complete tree, the largest node in this tree is this guy right over here, and the last node that would be returned here is the last node in that traversal would be this one. So number 3 doesn't always work. 1 on the other, so consultant 1 is always correct. So the answer is A. All right. With a formally chosen hash function, it's possible to have a situation in which the search time in a hash table of n items goes to flux. What's the worst case scenario for our hash table if we've got a bad hash function? Which of these times is the worst case scenario for a hash table when we have a bad hash function? Not O of n factorial. O of n factorial would be something like it's like Bogos work. We have to provide, or basically we're trying all possible combinations.
O of n squared?
O of n squared would be made basically for each item we would have to check each item, so it's not O of n squared. No, constant time is the best time.
And O of n, you're still
Yeah.
one at a time.
O of n is the worst case. Sorry, O of n is the correct time. It's the worst case scenario for this. It's A. It's A, right? Because what happens when you have a bad hash function? Say like, let's hash everything to 0. In that case, so what happens in that case? Right, we would have a collision at index 0. Sorry, we'd first insert our first item over here at index 0 and we'd be fine. Let's insert our second item. We'd get an immediate collision over here, and that's okay, we'd go to index 1. Then we'd get, when we insert our next item, we'd have a collision, then a collision, but that'd be okay, we can insert here. Then we'd have a collision, 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 and we'd insert here. Then we'd have collision, 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 collision. We'd insert here. Collision, 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 collision. So if there were n items already in the hash table, we'd have n collisions when we have a bad hash function. All right, so nodes for a doubly linked list are defined by the following structure, right? You've got your data on top, then you have your next pointer, then you have your previous pointer. So below is a list of, here's a list of nodes, right? This is node n, this is node p, right? N's.next is p, and P's.next is this third guy, and then they've got their previous links, right? Just a list of 3 items, one of which is defined as n, one of which is defined by p. So which of these is not the third node in the list? Which one of these is not the third node in the list? For instance, p.next, that is the third node in the list. So p.next.next, that's also the third node in the list. p.previous.next, that's p, so that's probably the answer. p.next.previous.next, that's the third node. And then n.next.next.previous.next, that's the third node in the list. So the answer is C. Now, question number 7 is definitely another good one because it's very similar to questions I'd like to ask for our scenarios. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets so it can be determined very quickly whether or not a given license plate is in the database. Speed of response is very important. Efficient use of memory is also important, but not as important as the speed of the response, right? They're saying, here's our priority. We want to get our answers back fast. That's the most important thing. We also would like to save memory, but if we have to make a trade-off between speed and memory, we are going to go for speed, right? That being said, don't just waste memory willy-nilly, okay? Which of the following data structures would be the most appropriate for this task? A sorted linked list, a sorted array with 1,800 entries, a hash table open addressing 1,800 entries, 3,600 entries, or 10,000 entries. Okay? So let's go ahead and review them one by one. A sorted linked list does absolutely nothing for us. Bupkis. It is terrible. Abominable. Why is that? Because, well, let's continue on to number 2 and figure out why. A sorted array with 1,800 entries. We've got 1,800 possible license plate numbers, 1,800 entries, right? It's going to be sorted. So how quickly would it take for me to find if a particular number was in this? Not use a map. A map is for C, would be in C, D, and E. But for a sorted array, how long does it take? Not constant time. In the sorted thing, you have to actually search for it. What's the quickest way? So it's a sorted array. What do we use for searching? Not O of n. No, what algorithm? What algorithm do we use for searching? What do we use for an array? I see I have to go over this one some more. Okay, this one, the way, if you're searching for sorted data, you want to use binary search. Does everybody remember that? Binary search? I think we went over that.
3 months ago.
Yeah. Still remember it. It's the quickest way to search for stuff in a sorted field. It takes. How long does binary search take? Log n time. Right. So we can search. So we can find something in a sorted array with 1,800 entries in log n time. It's pretty nice. But on the other hand, a sorted linked list, doing binary search on that doesn't exactly work because we don't have. In an array, we have access to the middle of the list. In a linked list, we have to iterate to the middle of the list. And that just that will take linear time. So B is the most memory efficient. It is the most space efficient of the answers. But it's not necessarily the most sorry. It's not necessarily the quickest. So let's look at C, a hash table using open addressing with 1,800 entries. Well, we have 1,800 license plate numbers, and we've got 1,800 entries. We're going to be getting a lot of collisions here. So a lot of collisions. If it's actually all the way filled up, that's pretty terrible for the amount of collisions that we would get. So this would actually this actually has a pretty terrible runtime. But on the other, it's the parking lot analogy. If you're trying to find that one car and if you're trying to find that one parking space in an almost full parking lot, right, it takes a while. On the other hand, if we have 1,800, right, and by entries, they mean, honestly, it's better rephrased as a table size, right? So if you have 1,800 license plate numbers, but your table is 3,600, if your table size is 3,600, that means half of the spots are empty. That means that collisions get very, very quickly resolved. In fact, you should be only having one to two probes on expected, so it will go by very, very quickly. So D is possibly the best choice. Yes, E would go a bit faster. However, it would waste a lot more space than it needs to. A lot more space. Right, and for almost no improvement whatsoever. All right, number 8. A Huffman tree is constructed for a text document containing 5 characters. The character E appears the most frequently, and the character I is the next highest frequency. Which of the following could be a Huffman tree for this document? So, 1, 2, or 3, which is a Huffman tree for this document? So one of these is not a Huffman tree. Which one? The first one is not a Huffman tree for this document. Why? What's wrong with it? The T shouldn't be there. Or the I, right? For a Huffman tree, the symbols have to be in the leaves, right? So this won't work as a Huffman tree. Now, 2 and 3 are Huffman trees, but they're not necessarily Huffman trees for this document. The most common character in the document is an E. So which of those, which reflects that, 2 or 3? 2, right? The most common characters, they have less bits, therefore they're closer to the root of the tree. So 2. In this one, E and I would be the least common characters. Here, E is the most common, and then it said that I is the next highest frequency. So that's reasonable that it could be on the same level as those. It means that these characters appear just about as much as E does combined, or E possibly occurs more than them all combined. An array of 7 integers is being sorted by heap sort. After the initial phase of the algorithm, which is constructing the heapify step, which of the following is a possible ordering to the array? So first off, heap sort, what kind of heap does heap sort use? A maxi. Maxi. So it uses a maxi. So we can already rule out one of the answers, which is D, because that one's a min heap. Actually, it's not even a min heap. It's not a heap at all. So in a maxi, the biggest value is at the top, right? So this is before we sort everything, because if it was sorting everything, you just simply check which one was in order. Here we're about to start sorting things. We want to know which value is the biggest. So the biggest value is at the root, and that's true for all the heaps and subheaps. So this is fairly straightforward if we just draw that, right? So let's go ahead and start with the first problem, because it's very easy to just draw a heap, right? You start at 85, and then 78, 45. This is still a valid heap, right? It's bigger than the thing in the root is bigger than everything else. 85 is the biggest number, if that makes sense. Then we've got 51, 53, 47, and 49, and we know this isn't the max heap because 45 over here is smaller than its children, mistake in that one. In C, we note that basically 49's children are 51 and 53. 49's children are bigger than it. And then in E, let's see, E, 51, one of his children, 53 specifically, is bigger than it. All right. Final and last multiple choice question. The binary tree, search tree below was constructed by inserting the sequence of items into an empty tree. Which of the following sequences will not produce this binary search tree? So in other words, this is a binary search tree. This is kind of like the reverse of the question you got asked on your exam, for an exam 2, right? Given a sequence of numbers, draw it. Here I'm saying, here's what I drew. Which of these is not a sequence of numbers that would have resulted in this, right? Now, actually, I like this question. I might steal it for next semester's exam, too. So let's go ahead and just look at this. So we've got 5 at the root for all of them. So let's start with A. 5, 3, 4, 9, 12, 7, 8, 6, 20. Those all worked. Nothing was added out of order. So now let's start with B. 5, 9, 3, 7, 6, 8, 4. We already added 3, so that was kosher. 12, then 20. Then for C, 5, 9, 7, 8, 6, 12, 20, 3, and then 4. Then for D, 5, 9, 7, 3, 8, 12, 6, 4. The hardest part of this is just keeping, I've got a large screen. Oh, I can just look at my screen. That makes it easier than trying to look at the projector. And then 20. Okay, so now for the last one, 5, 9, 3, 6. 5, 9, 3, 6. What just happened there? We skipped 7. So 7. So E will not construct it. It would give us 5, 9, 3, then the 6 over here, then a 7, then an 8. So it would actually be a much bigger tree. It would be a taller tree. All right. So answer the 3 of the 4 questions in the space provided. Trees. 1. Suppose the keys in the middle row of a standard keyboard, A, S, D, F, G, H, J, K, L, are inserted in succession into an initially empty binary tree. Draw the tree after the series of insertions has been made. That's something that was on our second exam, so it's not really too hard. So it's a very lopsided tree because of the way it works, right? S is bigger than A, D is less than S, A, S, B, F, and then what's after those? G, then H, J, K, L, right? Right, all those are it's just successively bigger. It's a pretty terrible jagged tree. This is like why we have, self-balancing binary search trees. Right, and this is what I mean, like when you can go and look up exams for stuff that we didn't really cover and just skip it, right? Right, you might remember, like, now try it with a 2-3 tree. And I briefly mentioned that 2-3 trees are a type of self-balancing search tree. We just never really went over them. That's perfectly okay, so we'll just skip that. Okay? Now this section is actually possibly the most important over here of these because this is most like the question that's most like another question that you'll actually get on the final. Specifically, this is the kind of question you will get for hash. Okay. So, you are given an empty hash table of size 7 that uses open addressing. We will insert the following items we'll insert a bunch of items that have the following keys. 15, 17, 8, 23, 35. Insert these keys using the following approaches. If an overflow, in other words, a collision, if we have to resolve a collision, indicate where we had to resolve the collision and indicate what caused it. Okay? So every professor has that last bit a bit differently. So let's start with A. We're going to insert these keys. We're going to use the hashing function. So we always provide a hash. Your professor will always provide a hashing function with this kind of question, where they'll say, and our hashing function here is given a key x. The index that we want to put it in is x mod 7. Resolve any collisions using linear probing. So let's go ahead and put it on the board. 0, 1, 2, 3, 4, 5. Okay, and let's go ahead and put that on over there. So, the first item to insert is 15. So what is 15 mod 7? 15 mod 7 is 1. So 15 mod 7 is 1, so we want to put 15 into index 1. Okay, next number is 17. What is 17 mod 7? 3. So we'll put 17 in index 3. 8. 8 is, what is 8 mod 7? 8 mod 7 is 1, so it puts 8 in index 1, except we can't, right? It's taken up. It's taken up. So there's a collision here. How do we resolve this collision? Where does 8 go? It goes in the next available space. That's what linear probing means, right? Open addressing using linear probing, we have a collision here, and I'll just indicate with an arrow. Right? Now let's insert 23. 23 mod 7 is what? 2. So we need to put 23 here, except we can't. The space is taken, so we're going to take the next available space, except we can't. It's already taken. So we'll take the next available space. So we'll put 23 over here in index 4. So, right? And I'll just draw an arrow to show that there were a couple of collisions. Do that. Okay? Next one is 3. 3 mod 7 is 3, right? Fairly easy math over there. 3 mod 7 is 3, so we'll go ahead and put 3 over here, except we can't. We have a collision. We have a collision here, so we'll put the 3 over here. And finally, we'll insert 5 into index 5, except we can't. 3 took our space, so we have to put it over here into 5. Right? So that's the way that kind of works. Okay? So that's with the linear probing, which is what we've learned, and that's what we test on. Now, just to make sure we've got the concept, let's just take a look at how it would work with quadratic probing. Okay, so let's go ahead and take a look at how it would work with quadratic probing. Now, with quadratic probing, right, in linear probing, we were looking at, well, if I couldn't have space I, I'm looking at I plus 1, then I plus 2, then I plus 3, and then I plus 4. Quadratic probing says, if I can't have space I, I'm going to look at I plus 1 squared, then I plus 2 squared, then I plus 3 squared, and I plus 4 squared. And including wraparounds, right? So wraparounds occur. So same values, we'll start off by inserting 15 and 17, just like we did previously. 15 goes into here, 17 goes into here based off of our previous answers. Now when we insert 8, we try to insert 8 mod 7 goes into index 1, but we can't, so we look 1 squared away from our initial position. So we just put it over here like we did last time. Now let's insert 23. 23 mod 7 is 2. 23 mod 7 is 2. So we want to insert it into index 2, but we can't. So we have a collision here, so we'll look at the next possible place to put it. Except that won't work. So we looked 1 squared away from our initial position. Now we need to look 2 squared away from our initial position. So 1, 2, 3, 4. So put it over here. Yeah. Into quadratic probing. The disadvantage, the reason we don't necessarily always use quadratic probing is that it can take a bit longer to do mathematical computations, right? Because you have to do a multiplication operation in there to do the squared. Right. So we didn't learn about double hashing. That's like just having a backup hash function. So let's go ahead and now take a look at graph algorithms, something that we had done, we had just done previously, we had been doing earlier. Yeah. So here is a depth first, so here this is question 1, or A. Oh, let me go ahead and remember to. So on this graph, we want to perform a depth first traversal starting with vertices C. Now, interesting, it has edges because we're going to use those. Select the smallest edge first when appropriate. In other words, right, I typically tell you to break ties using alphabet, by going in alphabetical order. Here it's telling you to break ties based on the weight of the graph, on the weight. Okay? Select the smallest edge first. In the space below, list the vertices in the order they are visited. Right? So we're going to start at vertices C. Actually, let's go ahead and actually do this on the computer with like a... Okay. Come on. All right, let's shrink this down. All right. So let's go ahead and put down an answer for this one. So we're going to start at C. So obviously that's our first node to be in. So let's look at C's neighbors. C's neighbors are, it can go to B, E, or F. So we got to select one path to travel down first. We want to select the cheapest path, which is C to B. So we select B. So now we're at B. So now we have 5 edges to choose from B. We want to choose the cheapest one, but we happen to have seen B to C before. So let's see, 13, 17, 20, 18. So we choose the edge with the weight of 13 and go to A. A has 2 edges, 13 and 10. We've seen the edge with 13 on it, but not the one with 10 on it, so we travel to D. Now we've traveled to D. We have the edges with 10 and 17 that go to A and B, but we've already been to A and B, right? So we're at a dead end, right? We went C, B, A, D. So now we're at a dead end for depth first search. So here we would pop back to A, which means we'd pop back to B. So we've been to A and D, but we haven't been to E or F yet. So then we'll go to F next because that has a cost of 18. That's a dead end, so we'll pop back to B. There's one corridor remaining for us, so we travel down the corridor all the way to E. That's a dead end as well because we've been to E, B, or C. So we pop, and then we go on to, so then we're back at C where we started, and then we have nowhere else to go, so we pop. So we visited C, B, A, D, F, E. So notice this is the reverse of the way I asked on the quiz. It's asking for the order which we visit stuff, not which we pop it off. Right? Now on the exam, you don't have to worry about it because I'm not asking a depth first search question. I'll be asking the next question, which is breadth first search. Yes?
Since you just brought that up, for the homework, should we put it in stack order? Or
I don't care.
Okay.
Because that depends on the problem you're trying to solve.
Okay.
Right? The depth first search, that again, you codify your output based on what you need. Or you create your output based on what you need. So unsurprisingly, the next question is, so same question, but now let's do a breadth first search. So again, we're going to be solving with C, but we can kind of pre-solve our question, right? Because we know what C's neighbors are. They're B, E, and F, and then A and D are the neighbors that, A and D are the neighbors that are 2 steps away. So we have our one-step neighbors and then our 2-step neighbors, right? Our neighbors and our neighbors of our neighbors. But that's not enough because we got to know the exact order. But we know that it's going to be some permutation of this group and some permutation of this group. So C. So of C's neighbors, which you've got 5, 20, a cost of 5, a cost of 22, and a cost of 30. So 5 is the cheapest, so that should go first. Then E is the next cheapest, and then F is the next cheapest. So turns out I put them in the right order. So then the neighbor, then we travel to B because that's the next step for this. And its neighbors are A and D with 13 and 17. So our order is C, B, E, F, A, D. So I just happened to have just jotted them down in the right order. All right, finally, the last question. Suppose you're using Dijkstra's algorithm to find the shortest path from D to E. List in the order which they become known all vertices to which the shortest path is determined in the process of solving this problem, and the length of the shortest path to each of these vertices. So I'll just go ahead and perform Dijkstra's algorithm as regular, and the answer will just simply be, we'll simply get the answer for free as I perform it. Right. So, right, for Dijkstra's algorithm to initialize it, I need 4 data structures. I need a set, a map, a map. Right. Dijkstra used a set, an array, but I'm using maps because they're cooler. Okay. So, and we're starting from node D, I believe. Yeah, we're starting from node D in this one. So we're starting from D. Okay. So, our first set is done. Okay. And we're starting from C. Starting from D. And then our second set is to do. Right? Where we're going to start from, and then that's everything else. So that's A, B, C, not D, but E and F. And then we need our maps. We've got our distance and our predecessor. How we got to this node. The nodes being A, B, C, E, and F. Right, so let's go ahead and let's finish initializing all these. Anything that that D has a direct edge to, I go ahead and put down. D has an edge to A, so I'll put down 10, which we got to from D. And B has a edge of 17 that we got to from D. And then everything else we simply put down a cost infinity cost to get there. And we simply say we got there from D. Okay. Yes? So now we start by, so that was initializing it. So now we start our algorithm. Of these, which has the cheapest cost? A does, so we found the shortest distance to A. So moving up to the done, right? I'll put a little dot here to give me a visual indicator to skip over this next time around. So now let's see if A adds any additional information. It has an edge from A to D, but we've already solved the shortest distance to D, so no point in adding. And then an edge from A to B, which would be 10 plus 13, which is 23. So is 23 bigger than 17? No, so we don't want to use 23 is bigger than 17. Yes, it is. So we don't want to use 17. So we don't want to use 23. We don't want to use that edge, that 13 cost edge to go from D to B, right? Really what I should be asking is if the cost is less than, right? So now let's go on to B. So, now let's look at all the remaining ones. Of these remaining, which is the cheapest cost, that's B. Okay. Next. So let's look at B's edges. B has an edge from B to A and B to D, but we don't care about those because they're going back to something we've already solved. B to C has a cost of 5, so that would be 17 plus 5, which is 22. Now is 22 less than infinity? 22 less than what we have now? It is. So we'll say we'll get to 22 via B. Now for E, that is 17 plus 20, which is 37. also say we can get there from B. And to F, that will be 17 plus 18, which is 35. And that also just happens to be less than infinity. Right? So we've updated all those routes. So now of those, so for of C, E, and F, let's see, which one is the cheapest? C is, with a cost of 22. So put C here. Okay. So we'll put C here, and now let's look at C's additional edges. So C to F, that is 30. So 30 plus 22 is 52, which is bigger than the cost I have for F. And then from C to E, that is 22 plus 22, right? 32. So C to E is 22, and then costs 22 in the first place to get to C, which is 44. So that's all bigger than what I have for E. So we don't update anything from C. Now let's take a look at E. So now, let's take a look at F, because that's the next cheapest form, F. F's, its only edges go back to solved nodes, so we're done with F. And then we're done with E because all of its edges will go back to only solved nodes. So that's our answer for Dijkstra's. It's not a particularly hard algorithm, it just gets tedious towards the end. Okay, the next page is prims, Kruskal's, and minimum spanning trees. We haven't gone over those, so don't worry about those. I decided to go over topological sort instead. All right, so now coding. This part of the exam deals with binary trees constructed of nodes that have a key and a data, and a left and a right. So in other words, these nodes are for like a tree map, right? These are maps that are used. So these are maps that are solved using a tree rather than a hash table, right? But otherwise, the only difference is that, that rather than having just one thing stored in the tree, it has two things in each node: the key and the value. So here's the following Java method that uses recursion to search for a key in a binary search tree, right? With parameter root. Should look fairly straightforward. Here's the node. Here's the key we're looking for. If the root is null, return null. Otherwise, if the key is equal to the key in the root, return the data associated with that key. That's the only difference from our standard search algorithm. Otherwise, if the key is smaller than our key, go to the left. Otherwise, go to the right. Okay? In the space below, do what I've always told you never to do, which is to write search so that it uses iteration rather than recursion. Right? Always told you never to do that. It's actually not so bad. And the reason that and you can write search fairly straightforward without having any recursion. The reason I've told you never to use recursion is because we were trying to learn recursion, right? But search is fairly straightforward to write with using recursion. So public static scratch.java. Let's go ahead and make this just quickly, scratch.java. Public static object search node no node E, just node root E, nope, not E, int key, because they're using ints for their keys. Okay, how is this going to work? So to do this problem over here recursively, we need to, I just want to make sure, to do it iteratively, we need to it's actually fairly straightforward. While root is equal to null, or rather not equal to null. While the local root we're on is not null. if we ever break out of this loop, we've hit null, so we return null. So while root is not equal to null, what do we want to do? If key is equal to root.key, then congratulations, I found the key. So return root.data. Else, if key is less than root.key, that means I have to go to the I have to search to the left. And the way I'm going to do that using iteration rather than recursion is I'm just going to simply say root is equal to root.left. Else, root is equal to root.right. So this one was a fairly straightforward one. Everybody clear on this one? Okay. The next one's a bit trickier. So let's write a Java method called mirror, which takes a reference to the root node of a binary tree and creates a new root, with its own nodes, that is the mirror image of the original tree. For example, if root is a reference to the tree on the left, then below is what we'd get when we return. Hint, the method is easier if we write using recursion. So I'm going to go ahead and just write it incorrectly first. Public static node, or rather correctly, but not address the prompt. Right, public static node mirror root. Right, which means I want to flip everything in this one. So if root is equal to null, I'll just go ahead and return null. That's generally a pretty good base case if I've got to return a node. Okay. Otherwise, what do I need to do? I need to swap my left child, my right child, and then tell my left child and right child to do the same thing. So node. So this is going to be incorrect though. So just hold on. If you're trying to copy down stuff furiously, hold on. So node. So let's say node temp is equal to root.left. Root.left is equal to root.right. Root.right is equal to temp, right? That swaps my left and my right. And then mirror root.left mirror root.right. And I guess I'd return myself, because why would I need to return myself in this? Hold on a second. And the answer is, oh wait, because while this does mirror everything, right? It swaps everything, my left and right. It swaps my children's left and right. It missed something. And it creates a new tree with its own nodes. That is the mirror image. So that we need to solve that one, right? Okay. How do I do that? So I guess I'll go ahead and delete this. So I'll need a node new root, and that's equal to okay. So I need a new root for myself. So that's going to be equal to new node root.data, right? Because I need to make a copy. Then node new left is equal to, well, so actually before I solve this recursively, I need to think about what my recursion is. What should my recursion be? So I need to generate a copy of myself. I need to generate a reversed copy of my left subtree, a reversed copy of my right subtree, and attach them to myself, right? So which of those is easy to do, right? Which of those is an easy thing to do? Make a copy of myself, right? Then then figuring out the, then creating a copy of my left subtree and my right subtree, that's hard. I'll figure that out in a bit, right? So node new left is equal to blah, node new right is equal to blah. And then then I would want to do new root dot right is equal to, sorry, new root dot left is equal to the new left, and new root dot right is equal to the new right, and then return new root, right? So all I have to figure out now is how to generate these things, and I think I'll just, and actually the recursion will handle it for me, is equal to mirror new, so it's going to be equal to root, the original root dot right, right? My new left is going to be the mirror of my right side, and my new right side is going to be the mirror of my original left side. And what each of my subtrees are going to do is that they're going to make a copy of myself, ask their own children to make to mirror themselves, and then they'll attach. And notice that they'll right over here and the left match up, and the left and right match up over here. So that ensures how they're going to. That ensures them swapping. Which I can actually shorten this up quite a bit by saying, can actually shorten this up pretty decently by saying new root dot left, new root dot right, by doing that. Because remember, I return a new node each time. So that will reverse it. Any questions on that? On that one? All right, final question of this practice exam is, what is the running time of your implementation of this method? What's your runtime of it? Well, how many so there's n nodes in there, right? How many times did I touch each? What did I do for each node? I made a new copy for each node, and then I just swapped my children, right? That was essentially 3 operations per node. It's a linear amount of work for each children, right? Having one more child equals one more node to swap, or one more node is equal one more swap operation, right? I'm not hitting each node more than once. I'm hitting each node, I'm doing like 1 operation per node. So it's reversal, so it's O of n time. This is an O of n algorithm, linear time. So that was one exam already, and boom, we're done. That was a 2-hour exam. And I think I did that in like an hour, so. I mean, yes, I did skip over some stuff that we hadn't gone over, but that would have been 5 minutes per problem. So let's go ahead and take a look at one more of these guys. Not this one. So I'm going to look at one that's not, I've always found this one to be a bit more, this one's much more of an algorithms exam because it talks, right, it's algorithms and data structures, right? So it talks much more, so over here it talks much more about notation and stuff like that. But it has some stuff that we didn't have in our other stuff, like problem 1 over here. Consider problem 2. It's a bit obtuse. It's a bit of an obtuse way to putting it. Consider insertion sort and merge sort. For each algorithm, what will be the worst case asymptotic upper bound on the running time if you know that additionally that? So in other words, what's the worst case scenario for the runtime if you know that under the following conditions? A, if you're doing insertion sort or merge sort where it's already where the input's already sorted. B, it's reversely sorted. Or C, it's n copies of the same number. Right? So all it's asking is like, okay, so let's go and tackle insertion sort first. What is the behavior of insertion sort if the input is already sorted? What's the runtime for that? Right? What does insertion do? How does insertion sort perform if it's given a sorted list? Yes. Not O1. Not O1. It's sorted, right? But it has to figure out it's sorted first. How does it do that?
So,
Yeah, O of n, because it checks each item. It basically goes through each item and says, oh, I can't push it down into the sorted section, right? That's the way insertion sort works. It can't push it down into the sorted section. So it goes through each item and checks it sorted. Just like similarly for bubble sort, where it will go through and say, oh, I can't swap anything because nothing has to be swapped, so I'm done, right? It takes O of n time to check if something's sorted. Now, B, the reverse sorted, is if you remember from my lectures, is that it's the worst case scenario always. Reverse sorted, in other words, if we were past something that looked like this, right? Here's the worst case scenario for insertion sort of a size 5. 5, 4, 3, 2, 1, right? We split it up for insertion sort. We have the sorted section, the unsorted section, right? So for the sorted section, so what do? We have to push the first item in the unsorted section down into the sorted section. So we swap 4 and 5. Then we have to push 3 down. 3 swaps with 5 and then swaps with 4. So it'd be 3, 4, 5. Then 2 has to swap with 5, then with 4, then with 3. So it will end up at the beginning. And then 1 has to swap with 5, then it has to swap with 4, then it has to swap with 3, then it has to swap with 2, all the way to 1, right? Everybody clear on that for insertion sort? Right? So if it's reverse sorted like that, then you have to, so if it's reverse sorted, that means that we have to do 1 swap for the first item, 2 swaps for the second item, 3 for the third, 4 for the fourth, and so on and so forth, all the way up to n. 1 plus 2 plus 3 plus 4, all the way up to n, so that's n squared total swaps, right? O of n squared total swaps. So it's O of n squared. Finally, if C is a list containing n copies of the same number, in other words, what if we had a list with 1,000,000 5s in it, right? What if we had 1,000,000 5s in it? Well, I'd argue that it's sorted, right? It's sorted. It's all the same number. Nothing has to be moved. Nothing has to be swapped. It's all sorted. So it reduces to, so C, previous answer to answer A, right?
do they mean that, or they mean that just like within the list?
That's a good question. Contains n copies. I assume it's my scenario because I'm the one talking in front of you guys. But that's good. The reason is because I assume that since we're talking about runtimes in terms of n, right? So n items, n copies of the same item. I'm assuming that's a list of them. Now, if it had like a bunch of copies, I don't really know how that would affect it. It would make a huge difference for our insertion sort. But on the other hand, for merge sort, what is the runtime for merge sort? N log n. Does it matter? Worst case scenario. So if it's sorted, does it matter? No. If it's reversely sorted, does it matter? If it's a bunch of copies of the same item? No. Merge sort is the apathetic to any runtime, guys. It's the apathetic sorting algorithm. It always runs n log n. Always, always, always. Because it just doesn't care what's within it. It will sort things in n log n time. Right? Because it just doesn't care. All right, so now, I also liked question 5 on this one. Suppose you have a hash table and you inserted some elements, and then you take a look at it. You're a good student, so you inspect it, and we look, and the result looks like the picture below. And you realize that there's a problem. A, what is the problem? B, give an example of how we got there, what hash function gave us the problem. And C, what's a better hash function? Answer each question in one sentence. So this is our table. So before we start off with like, we'll start off with like, negative Z, I guess, before we hit A. What is the collision, what kind of collision resolution are we using here? We're using chaining. This is a hash table that uses chaining to resolve its collisions. Okay? So, what is the problem with this? What is the problem in this specific hash table? Not with like chaining, but like this particular hash table. What was the problem? Yeah, everything's even ending. Very good observation. Everything is ending up in even bins, right? Everything's ending up in an even index, right? Nothing ended up in an odd index. Or if you want to be even more general about it, because that was a very specific answer. You want to be very good observation there. If you want to be more general about it, there's lots of collisions and relative to the amount of empty spaces, right? So, okay, that leads us to part two. Give an example of a hash function that could give rise to this behavior. What could have gotten us here, right? You mentioned that basically we're only using even indices, but there's a reason for that. What is the my night light is on. That's why the color changed and got weird. So give me 1 second to night light disable until tomorrow. That should be a bit easier to read. Okay, so what hashing function results in this? So yes.
It looks like you're taking the single digit and just multiplying by 2.
Yep, you're taking the ones place and multiplying by 2. Exactly right. So right. So we're taking this. So for instance, everything ending with 0 ended up in index 0. Everything ending with 1 ended up in index 2. Everything ending with 3 ended up in index 6. Right, and so on and so forth. So specifically, the hash function here was h of x. It looks like a possible hash function for this was h of x is equal to x mod 10 times 2. Take the last digit, multiply by 2. Right, that's a hash function that could have given us this. So what would be a better hash function? I mean, your answer could, technically, literally anything else would probably, literally almost anything else, because, again, h of x is equal to 0 wouldn't be a better one. But what would be a better hash function? Right? H of x is equal to what? What would be a better one? Well, let's see. The size of the table is 20, so we could just do x mod 20. That probably would give us something better. At least we'd have a possibility of using all the spaces. If we really wanted to make sure that we weren't getting into something weird using prime numbers, we could just simply write off as a loss the last spot, 19, and we could just do x mod 19 so that everything would be modded by a prime number, thus reducing the number of collisions.
In general, is modding by the table value like the basis of all the hashing functions?
Yep.
We shouldn't be really looking.
That's because hashing functions have multiple parts. You have first you have to generate the hash code, and then you have to modify the table size, which is generally the way it works.
But if we're like asked to provide like a hashing function that would be better,
You won't.
to table size, that like we should be thinking about like multiplying.
No, you shouldn't be. And you won't be asked for something better. I should know. I'm writing the exam. Right. This is just a very good question. I just thought this was a very good question because it asks you to solve a problem. Okay. And then let's see, what time is it now? 4:43. So suppose we have the numbers 1 and 100 in a binary search tree, and we wanted to search for the number 45. Which possibly multiple of the following sequences could be the nodes examined, right? So we're storing 1 through 100 in a binary search tree, want to search for 45. Which of the possible of the following could be a sequence of nodes examined? So let's see. So for instance, starting at the root is equal to 5, right? The first node we'll check is the root. So we start at 5. 45 is greater than 5. So we should go to the right, except we ended up at 2. So that's not going to work. Okay? Let's go ahead. 1 is the root. We could look at 1 and then go to the right. Then we could look at 2 and go to the right. Then look at 3 and go to the right. Look at 4 and go to the right. Go look at 5 and 6 and 7 and so far and keep going to the right. Right? That's a possible, like, really badly balanced tree, but it's a possible search for 45 before we determine it doesn't exist. Right? So we could start at 9, then go left, except 45 is bigger than 9, so this won't work, right? Here we're going left to 8, so that wouldn't work. Starting at 8, going left to 7, going left to 6, 5, that won't work either, searching for a number that's bigger. Starting at 50, going to the, going to the left, because 45 is less than 50, so we end up at 25, going to the right, going to the right, going to the right, going to the right, and then this one won't work because then we'd go left for looking for a number that's bigger than 45. Here on the final one, though, if we took that off, this last sequence of searches would work. Everybody kind of understand this one? Here we'd start at 50, right? Here it's saying the root is 50. We go left, we'll hit 25. That's a valid move. If we go right, we'll hit 26, also valid. If we go right, we'll hit 27, also valid. If we go right again, we'll hit 40, also valid. If we go right, we'll hit 44, that's also valid. But here, if we were going left to hit 42, that wouldn't be valid because we were searching for 45. We wouldn't go to the left to search for 45. Okay. So, let's see. So that's what I've got here. So, it's 4:46, so might as well. So we'll do the other 2 exams on Wednesday. Okay.